So we have this expression right here. So how would we go through and give this something nice? Yeah, well, okay, so what you could do, right, is take this thing, turn it into polar, multiply it by 5, and that'll work, right? But then once you did that, you'd end up with a polar expression here and a rectangular one here, right? So then you could do like this to polar, to rectangular, to combine, back to polar, right? I mean, so this is where, again, right, doing practice in this class really helps. So I'm going to say, in this case, right, it might be more fun to do this. Let's see, so we do a complex conjugate thing. That might be faster, right? I mean, I don't know. I'm just thinking it probably will be looking at it. So the way I did it in my notes is I took that expression, turned it into polar, multiplied them, then turned the whole thing back into rectangular, and then subtracted them, and then polared it again. So let's try the complex conjugate way instead. Because what's our ultimate goal here, right, is to get it as one big complex number. So let's try it a different way. Okay, so let's see. Let's try this. Where's 100J? Okay. So in this case, right, the bottom is just going to end up being what? Yeah. So, well, if you want, it's going to be, the cross terms should cancel. You'll get 10,000 plus 10,000, so you get 20,000 over 10,000 minus 10,000 j times 5 minus 5. So, yeah, am I messing up?
Well, wait, why are we trying to find VLS2? Aren't we trying to find VX because we found VX there? And like...
Well, there would be fine, right? In this case, right, let's call this thing VY. How are VY and VLS1 related? VY is that one. Okay, sorry. So this is VY. And here is VLS1. How are those related? Yeah, exactly. Yeah. So on that side, they're the same. Okay, so do some algebra. So you can kind of get a flavor for where we're going here. I mean, I don't really want to grind through this anymore. So you can do more stuff, and you'll get 5 over root 2. Because I want to get to more interesting things than watching me do algebra. Okay. So you can eventually get to this point. It's not hard. That's what all the homework's for, to prepare you for that. Okay, so ultimately then, what will VL of t be? So we kind of have, this is V at LS2. Assuming I didn't mess that up, it'll be, so this thing, right, it'll be what? What do we get? Oh, you got it already, 3/10 cosine 10t plus 1.47 plus what? Yeah, okay, if I root 2 cosine, okay, so what's the omega here? Yeah. All right, cool. Okay, so we've now shown that this thing, we can solve it even with these 2 different voltage sources. Okay, cool. So then you know the voltage there. That's a slightly harder example. It's really hard to make them much harder than that because of the fact that kind of the curveball is having multiple frequencies. Everything else is just node voltage. Go ahead. Okay, yeah, that's a good question. What is this thing right here? Is it the particular solution or the homogeneous solution or the complete or what? Yeah, this is the particular. Okay. In this case, right, there will also be a homogeneous solution. How would we find the homogeneous solution? You write out the ODE. And in this case, the ODE would not be very hard because you would take away the sources, ultimately. If you write out the ODE, you would zero out the sources, and you'd just end up with an RC circuit. Or no, actually, you'd end up with an RLC. So the ODE, the homogeneous solution will look like what? Just yes. Z left? I didn't really say it. It's those two guys in parallel. Yeah. So if you do the parallel function for them, you'll get that. 7 of them? Okay, yeah. So the homogeneous, right? Okay, so the homogeneous, what kind of circuit will you get? What kind of differential equation? First order, second order, what? Second order, right? Okay. So suppose you have a circuit with 80 inductors, capacitors, and resistors. Do you think you can find the particular solution if there's one frequency? It'll take you a while, but ultimately it would be a what? An algebra problem? A differential equations problem? Yeah, so particular solution, you can kind of, it scales. How about the homogeneous solution? If you had R, L's, and C's, like 80 of them, then what would it be? You'd end with a gigantic crazy ODE, right? So what we usually do is we assume that our system is such that we don't actually care. And I will, on the homework Friday, I'll talk a little bit about when that doesn't actually hold true. But it pretty much always does. Yeah, it would complete the homogeneous, yeah. But it says in steady state. That's the key. So in steady state means the homogeneous solution has died out. Yeah. Yep. You do not have to write a whole page of math. You can try. What's that? You can do 3 pages if you want. And then you can say, but in steady state, right? The idea is that the homogeneous solution has died out. Okay, so I'm going to talk a little bit about filtering so you guys are ready for Wednesday. So a lot of times we build circuits, right? So you guys now have the tools to understand how circuits will react to different frequencies. So a lot of times, we have a bunch of different cases where we want to think of not just how a signal reacts in time, but how it reacts as a function of its frequency. So, for example, right, when you have a set of speakers, what you do is you take your raw, 20 kilohertz of bandwidth of sound signal. What you usually do is you separate out the low and send it to the subwoofer and send out the high to the tweeters so they can do their respective jobs. You can send the whole signal to both, but it sounds nicer if you only give them what they want. You can also do it to remove noise of a particular frequency. So if you have small voltage, right, a lot of times you'll get 60 hertz noise in a lot of applications. You can filter that out. If you've done EE20, you have a flavor for how notch filtering, I think, maybe they talk about that, how it works. Or if you have some particular annoying sound, you can get rid of it. And yeah, so, this is kind of the same. Oh, so this is a little different because my idea here is that, if you have an antenna, right, an ideal antenna, it's technically, if it worked really well, it would pick up every single radio, TV, police scanner, whatever, all those things, every single frequency all at the same time, right? And the way that you go about listening to the one thing you want and not everything at the same time is you use this kind of filtering technique. Yeah. So filtering is definitely a handy thing. And this is going to be like one of the cool the cool things we could do with circuits, like this idea of generating a blinking light every time you get a bass signal, right? That would be hard to do with any of the tools we've done until right now. So here's an example of a filter. Looks a lot like what we've been doing before, right? There's not much to it, so I'm just going to PowerPoint through this because you know how to do it if you understood what I just said with the board example. So our goal here is to find what the capacitor voltage looks like in time. So replace by equivalent impedances, do a voltage divider, multiply out, and you get an expression, okay? And this is just what we've been doing before. So what we're going to think about now, though, is instead of necessarily having a one frequency, right, we're going to maybe have like a sum of many frequencies. And so what we're going to get is